So this is the last lecture, and today we are gonna hopefully get to say something about the Cyber-Witten solution of the low energy dynamics of n equal to SU2 theories. So let me quickly recall what we said in the previous lecture. So we were setting the stage for what we are going to discuss today. So we are studying, as we said, n equal to pure SU2. And in this case, we saw that basically we are dealing just with the n equal to vector multiplet, which is basically a chiral and a vector n equal 1 multiplet. And so we wrote down the n equal to Susy-Lagrangian for this theory, and we then argued that if we want to write down the most general non-renormalizable n equal to effective action, everything is encoded in a single holomorphic function, which is the prepotential. So we are interested in understanding what's going on at low energies. So when indeed we are going to write down a sort of Wilsonian effective action, and we know that this effective action anyways will be constrained to be of the most general form with generalized coupling and Kähler potential that are both written in terms of this single holomorphic function. So our job today will be basically to nail down the form of this holomorphic function. So we saw that this theory, the n equal to Super-Yang-Mills theory, has vacua, which are basically characterized by the waves of the scalar in the chiral multiplet, which can be, in the SU2 case, diagonalized to a traceless matrix. And so this is basically proportional to sigma 3. So these are the waves that parameterize the Coulomb branch moduli space. And the effect of this wave is to break the gauge group from SU2 down to U1. So we deal with an abelian n equal to theory. So this is what's going on generically for generic waves. And we would like to understand what happens at the quantum level as we move in the moduli space of vacua. So first of all, we define a coordinate u, which is the trace of phi square, as the coordinate on the moduli space. So basically, U is more or less a square over 2 classically. But then when we have quantum correction, is no longer 2, that the trace of the modulus of phi square is equal to trace phi square, obviously. And the reason why, anyway, we are going to take this a square rather than a as a coordinate is because this is a Weil invariant combination, because when we break down the gauge group by Higgsing, we still have a residual Weil symmetry, which in this case is just exchanging the sign of A. So I need to construct an invariant coordinate on the moduli space of vacua. So I choose to use a square, which is classically, it's U, but basically if I want to be able to use a coordinate also at the quantum level, I should better use trace phi square, which I call U. So we want to study basically the U plane, which is this moduli space of vacua. So at generic points where U is different from 0, we expect to find an abelian n equal to effective action. And classically, we expect maybe something is going on when U it's equal to 0. We have massless, non-abelian gauge bosons, because where I don't have a VIII, so I expect that since I'm not Higgsing down the theory, if I'm trying to describe my theory with an abelian effective action, I might miss some massless degrees of freedom, which are those of the gauge bosons. So the picture that we might have in mind at the classical level is that there is a singularity in the moduli space at U equal to 0, which is where I'm not undergoing this Higgsing of the gauge group triggered by the VIII. As we are going to see, this picture is going to be completely changed at the quantum level. So, as I was saying, then at generic points, you expect where U is different from 0, we expect basically an n equal to abelian vector multiplet. And then we know that the low energy effective action can be written in terms of the prepotential. And this is what we are gonna discuss in a moment. But first I want to remind you an observation that we had in the last lecture, that what is the fate of the a massive gauge boson that get a mass because of Higgs mechanism. So these were components of the massless n equal 2 vector multiplet, and then they just got a mass because of Higgsing. But then it would mean that they would sit into massive representations of the n equal to superalgebra. But as we have seen in the first lecture, massive representations have more states than massless representation. But this Higgs mechanism cannot account for missing states. So it must be that these massive gauge bosons sit in massive representation with the same number of states as massless representations. And this happens only if these representations are satisfying the bound for shortness. So they must sit in ultra short, which in the case of n equal 2 is the same as short, massive representations, which means that their mass must be given modulus and normalization in terms of the modulus of the central charge. Then I quoted a result by Olive Witten, which showed that if you calculate, you can calculate, in fact, what is the central charge. And basically what they did was to write down the supercharges in terms of elementary fields. So if you, as usual, a charge is always given by the integral of the time component of a current. So you integrate the time component of the supercurrent. So you write down your action, you do the Nether variation, you write down your Nether current in terms of the elementary fields. This gives you the supercharge, and then you can calculate the commutator, the anti-commutator, and this gives you an expression for the central charge in terms of the elementary fields. And in Olive Witten showed that the real part of this central charge is equal to A, which is the VIII of the scalar times the unit the number of units of electric charge, whereas the imaginary part of the screening charge is proportional to the tau classical and the units and the numbers of units of magnetic charge. So it means that if you have representations, massive representations, which satisfy this shortness condition, their mass is going to be given in terms of the central charge, that is in terms of their charges under electric and magnetic field. So in particular, we see that for W boson, the electric charge, it's 1, and the magnetic charge, it's 0, and then it's consistent, and M is proportional to A, which is the Higgs mass, as we were expecting. But then this fact is also telling us that there are massive magnetically charged objects in the spectrum. And these are supersymmetric monopoles and ions, and they will play a role today because we will be forced to invoke their appearance to have a consistent descriptions of the low energy effective action. So we will leave this observation here for the moment, and we will come back to these massive magnetically charged objects later on in the lecture to help us solving some problems. So as we were saying, the first thing that we can write down indeed is the low energy effective action in the region where we have indeed an abelian theory. So in this case, the effective action will be of this form. So we will have, I'm writing down, I'm specializing to the abelian case, the general form of the effective action that we have written a number of times for an equal to theory. So the second derivative, now I'm using this double prime index to indicate second derivative because I don't have many color indices. I'm just differentiating respect to phi, which is the chiral field. So the second derivative of the prepotential is going to play the role of the generalized coupling. And it is also basically giving the metric on the Kähler manifold. It's the Kähler metric, which is the metric on the target space of this nonlinear sigma model. So notice here that basically in the non-abelian case, we wrote 2GV phi prime with the usual minimal coupling. So now you see e to the GV, it's gone because as we mentioned, when you do U1, all the interactions are gone because remember that all the fields here are in the adjoint. So the interactions would be proportional to the structure constant, but now we are in the U1, so the structure constants are not there. So there is no interaction. It's a very simple, stupid theory. This low energy theory. So if we knew the function f, the prepotential, then we would know exactly completely the dynamics of this theory at low energy. So if we choose the prepotential in this form, this is we go back to the renormalizable UV action. So the form of the prepotential can be, in fact, fixed by non-renormalization theorems. As we will see, it is clear that since the prepotential, its second derivative is related to the holomorphic gauge coupling, and we proved already non-renormalization theorems for the normalization, for the holomorphic coupling, it's clear that there will be no renormalization theorems also for the prepotential. So let me anyway derive for you the renormalization theorem for the prepotential as proposed by Seiberg. This is work from the 88. So Seiberg argued that the general form of phi, it's basically only consisting of a one loop plus non-perturbative corrections. And the way he basically proved this non-renormalization theorem is to look at the U1R anomaly. So remember, in this n equal to theory, we have two fermions. We have the gaugino, and we have the Weil fermion sitting in the chiral multiplet. They both have R charge 1 under the U1R symmetry. So when we calculate our triangle diagram, we get twice, because the contribution of gaugino and psi, it's the same, times T of the adjoint. So this is 2 times T of the adjoint of ST2 with, in this case, it's 4. So this is a non-zero anomaly, which produces, as we know, a shift of the theta angle. So in this case, the shift is by 8 alpha. So it means that the U1R symmetry is broken to Z8 by the U1R anomaly. In fact, then we can also argue that when we turn on the VEBs, since the scalar has a charge 2, we further break the Z8 to a Z4. So the fact that there is this Z8 surviving part of U1R symmetry, in fact, also tell us that on the moduli space, there will be a symmetry that relates U and minus U. So the idea is that so the Seiberg argument goes more or less as follows. If there is such an anomaly producing the shift of the theta angle, I can track down, okay, where this shift comes from. So it means basically that the effective action will vary under the action, well, will vary as a consequence of the U1R rotation by something proportional to the coefficient of the theta angle. So the variation of the effective action will be proportional to FF tilde, which is multiplying this angle, which is shifting because of the U1R rotation. Then what is the part inside the lambda that can be responsible for the such shift? Obviously, just the part containing the field strength. So inside the effective action, I look for the part containing FF tilde. So here I'm doing the anomalous rotation on the argument of acting on phi on the chiral field. This multiplies the field strength and the FF and the FF tilde term. And then I removed the contribution without the rotation. So this is the part that should be responsible for the anomalous rotation that we are discussing. I'm keeping NC generic. This argument works for generic rank. So, okay, so you understand, this means that phi is rotating with our charge 2. So this basically is an equation for the prepotential, right? Because then I see that the second derivative of e to the 2 pi I phi minus phi, it's equal to minus alpha NC over 8 pi square ff tilde. So I can try to solve this equation, which is basically if I Taylor expand the second derivative of f, basically I get an equation for the third derivative of phi in terms of I and C pi over phi. Okay, this is just, I'm linearizing. I'm just expanding to, Taylor expanding to first order in alpha, this expression. Good. And then I simply integrate this equation to phi. This gives me the perturbative part of the prepotential. So there will be the three-level part. And then I will have a one loop contribution. Okay, so then there are no higher loop terms, and this is one loop exact. Now, notice if we want to play our usual spurious symmetry game. So basically what we have done now, we have found the perturbative part by requiring it to be consistent with the anomalous shift of the theta angle, which is a consequence of the anomalous rotation. But as we have done several times in this course, we know that if we promote lambda, well, we can restore U1R as a spurious symmetry if we require the scale to transform with our charge 2. Then you see that if you require this, that is that lambda is a spurious field that transforms with our charge 2, then if you do so, F, the prepotential, is an object with our charge 4, because it's quadratic in phi, which has our charge 2, and then you get only the combination phi square over lambda square. Now you can use this spurious symmetry, as we will see in a moment, to constrain also the non-perturbative part. Okay, the non-perturbative part has to respect this property of being over charge 4. So it has to be something which is still proportional to phi square. And then I need to cook up the usual instanton contribution, which contains the holomorphic scale, but I need to have it combine with the VIII of phi. Okay, so that you see that lambda and phi, they rotate in the same way. So overall, this gadget F non-perturbative will just rotate under U1R only as phi squared. So this constrains basically the form of the possible non-perturbative contribution so that it is consistent with the spurious U1R symmetry. So the obvious comment, obviously, the non-renormalization theorem we proved for F, it's consistent with the fact that the second derivative of F is just tau, and for which we already proved the non-renormalization property. Remember, we had this discussion last lecture that the holomorphic and equal to coupling is really exact one loop plus non-perturbative, and there are no issues about physical, non-physical coupling, because basically the anomalous shift that is responsible for this discrepancy in the n=1 case is not there, because on top of rescaling the vector multiplet, I need to rescale the chiral multiplet, and the two rescaling actually cancel out. So this is just one loop exact. So something that we need to keep in mind, however, when we think about the coupling, is that when I'm undergoing the Higgs mechanism, breaking the SU2 gauge group down to a U1, the coupling is actually frozen. So basically, let's discuss the gauge coupling for the SU2 theory. So you know that this is an asymptotically free theory. So the coupling becomes smaller and smaller when I get to high energy. Now imagine that somehow at this point I develop the VIII, and so this is the gauge coupling of the SU2 theory. Imagine that at a certain point I develop the VIII, and now the gauge group is 6 down to U1. But now, when I have this U1 theory, we already said a number of times, there are no interactions, because it's all the fermions and scalars that we have, they sit in the adjoint representation. So in the U1 case, there is no interaction. So being absent the interactions, there is no reason for the coupling to run. So when I undergo the Higgs mechanism, the coupling is actually, let me do it in red, in blue. So this blue line is actually the correct running, because here the theory becomes U1, and the coupling frees when I reach the scale of the Higgsing. So if I think in terms of coupling, basically my tau one loop as a function of the scale A will not be running. Okay, when I reach the scale A, then it stays like that. And you can check that this form is exactly the second derivative of the prepotential that we just wrote here. Okay, as fixed by the U1R anomaly. Whereas here I wrote this. This will be the running that we wrote in the previous lecture. So this will be the one loop running that is dictated by the U1 by the beta function, and beta B1 for this theory is just so we have the contribution of the vectors, and then fermions, . and then the contribution of the scalars. So in our case, we have the gaugino, the fermion in the chiral multiplet, and then we have the scalar in the chiral multiplet. Everything is in the adjoint. So this is just 2 and C. Okay, so this is just the one loop running that we expect with the choice of the scale mu as A. Okay, so what we have learned is that at the moment, it seems that everything is pretty simple. For large U, so when I'm away from this presumably problematic region where I don't have the VIII, so when U is large and A is large, and by the way, large A means that the coupling anyway is weak because it's an asymptotically free theory, so I can trust perturbation theory. So in this region where U and A is large, I can write the prepotential in this form. So this is the combination of the 3 level plus 1 loop. And I'm using A instead of phi, because in this region I can identify phi with its VIII A. And then I have the contribution of all the non-perturbative terms, the instantons, which we already discussed. They should come in the combination lambda over A to the 4K. That's what is allowed by U&R symmetry, with some coefficients. These we don't know. Well, maybe you can try to do instanton calculations, and in this regime where A is large, you could attempt to do that. And people did so. It's very complicated, but we're going to see a different way to fix all these coefficients. Good. So at the moment, the situation looks very good, but now we start seeing that there are problems. So the problems come from the following observation. So the imaginary part of the prepotential is basically the gauge coupling, right? And well, obviously, we need this object to be positive. But clearly, this imaginary part will contain something like the log of A over lambda, and this can be negative. So this can be negative, and so it's not clear, right, how we can satisfy the condition that the coupling is positive. You may think that maybe if you add the non-perturbative terms, then this thing it's positive. But in fact, there is a very strong argument that tells us that this cannot be everywhere positive. And the reason is the following. So instantons cannot help. So in fact, if f is a holomorphic function, as we assumed, then the imaginary part of f is an harmonic function. And basically, you can use a theorem in complex analysis, which is the minimum modulus theorems. That tells you that cannot have a minimum, this function. So it cannot be always positive. So the only way out is that this description in terms of f that we constructed cannot be valid globally. Okay. So it means that we will have to use the different descriptions in different regions of the moduli space, because if you try to extend your description everywhere in the moduli space with some holomorphic function f, then you will not be able to construct a gauge coupling which is positive. Okay, so to understand how to construct alternative descriptions which are valid in different regions of the moduli space, we need to first introduce another property of the effective action, which is the fact that there are equivalent descriptions, because we can perform transformations, the so-called duality transformations, that give us equivalent descriptions. So we can define sort of a Legendre transform. We can define a field phi dual as the derivative of phi, and phi prime, sorry, f prime dual, function of f dual, minus equal to minus f, where f dual, I want to think it as the dual prepotential, is going to be really the Legendre transform of the original prepotential in terms of the original chiral field phi. So I want to rewrite, try to go from the original variables to this dual set of variables. And the claim is that this is going to be providing a dual description of the field. So I need to see how this transformation acts on the action and on the Lagrangian. So let's first look at the part involving the kinetic term for the matter. So this we wrote as d2 theta bar, phi bar, f prime, f. So what I do, I use the definition of dual variables. So this is given by minus f prime d bar, fd, and then I integrate by part. And this is just phi bar dual f prime dual. So you see that I get exactly the same form of a kinetic term for the chiral field in terms of the dual prepotential. So this it looks very much like having done a canonical transformation where you set Q equal to P and P equal to minus Q in the phase space. And this transformation has unit Jacobian. But instead, the transformation of the part involving the kinetic term for the vector multiplet it's a little bit more delicate, and it is not a symmetry of the Lagrangian, it's a symmetry of the action. So I need to look at the integral over, sorry, it's a symmetry of the partition function. So I need to look at the integral over the fields. So I will have an integral over the vector field, which is so the exponential of x and pi, the imaginary part. So now there is a trick that I can play. I can introduce an auxiliary integration over dual V and integrate over dw. So the integration over V dual is going to play the role of a basically Lagrange multiplier. So I want to rewrite this as so basically, you see, if I integrate over V dual, has the effect of setting this equation, which is basically the analog of the Bianchi identity. Okay, because I cannot simply decide to integrate over the field strength W, because then I would miss this constraint. So this integration over the Lagrange multiplier is enforcing basically Bianchi, and then I can think of the integration on over the field strength rather than on the vector field. But then I now can manipulate a little bit the integrand to get to the dual action. So we rewrite this term that we add as so we do some integrations by part. Here I'm rewriting the integration over the 2 theta bar as a second SUSY derivative respect to the bar. Here I'm using that, well, now I'm going to use that W alpha is a vector superfield. So when I take d bar beta dot, say, of W alpha, you get 0. So I can take it out from this derivative. So I can get just d alpha d W alpha. So we are done, because now what we want to do, we want to claim that this is just -4 the integral in d2 theta of Vd alpha W alpha with the definition of the dual field strength, obviously as -1/4 d bar square d alpha V dual, which is as we define the abelian field strength. So you see, if we go back here, we see that if we do the integration over V dual, we go back to the original action, but now instead we want to go back to star and do the integral over dw. So now the integral for dw, once you have done this rewriting here, where you have rewritten this part in this form, is just a Gaussian integration. So we perform a Gaussian integration, and we get that we are left with the integration of the dual vector field of I over 16 pi, the imaginary part, d for x, d2 theta, minus 1 over f second of phi, v dual alpha, v dual alpha. Maybe the index is the other way around. Okay, so you see that this is again what we end up with is something that looks like the kinetic term for an n equal 2 vector multiplet in terms of where we have the dual field strength. But now the interesting thing is that the generalized gauge coupling for this theory, it's given by minus 1 over the second derivative of the prepotential. So we would say that in this theory, the dual gauge coupling, it's minus 1 over the second derivative of phi of the prepotential, which for us define the original coupling. Okay, so in this theory, you see what is going on is that if I go to dual variables, I end up with a theory where the gauge coupling, it's given by the inverse of the coupling of the original theory. So this is like indeed an electromagnetic duality. So if I go to dual fields, the coupling is flipped. And of course, also in this dual theory, I want to define the dual coupling as the second derivative of the prepotential, which will be minus d phi in d phi dual. Okay, so summarizing, we have a dual action which looks as follows. So we have 1 over 16 pi. So it looks like the electric action, but we have now everything written in terms of the dual variables. Sorry, let me write it. F second phi dual, W dual alpha, W dual alpha, plus d2 theta bar, phi bar dual, F prime d dual of phi dual. So this action is basically what we are doing is that we are taking the fields phi and phi dual and sending it to a new set of fields. So the claim is that this is the map to the dual theory. So if I perform this change of degrees of freedom, I get a dual description of my theory, which has the property that the coupling is going to be inverted. And this is like an electromagnetic duality. So in addition to this symmetry, there is another, in addition to this transformation, which is acting producing a dual description of the theory, we can do another transformation. We can take phi dual and phi and send it to the action of this matrix with B integer. And this is in fact a trivial symmetry of the theory. This is easy to understand because if we take the coupling, which is basically this is the second derivative of f respect to phi. The first derivative is phi dual, so this is d phi dual in d phi. But then if I do this transformation, this is just sending d phi dual in d phi, in d phi dual in d phi plus b, and b is an integer. And so if I shift the coupling by an integer, a real integer, this corresponds to shift. Okay, remember the imaginary part of the coupling is gonna multiply the topological term. So this is just corresponds to a shift of the ff tilde terms. So in the end, the effect of this transformation will be just a symmetry, because you will just get that the action is multiplied by an integer. So this is a more trivial symmetry that we have. This is just the possibility of, it's basically the symmetry sending the theta angle in theta plus 2 pi n times an integer. So this is a trivial symmetry of the Lagrangian. But then we notice that there is also another interesting transformation, which is instead is not a symmetry of the Lagrangian, but provides a dual description of the theory. That is, I can rewrite my partition function in terms of the dual variables, and I end up with a equivalent description of the theory in terms of these sets of fields, phi dual with a dual prepotential. So we are going to need this possibility of using different descriptions. And first, let me make another comment, is that if we look at these two matrices that generate these equivalent descriptions of the theories, we can say that these are matrices that generate the SL to Z group. So these are matrices with integer coefficients and unit determinant. So we have this SL to Z action on the theory, and this SL to Z action has the effect of producing equivalent low energy descriptions of the theory. So the message is that there is not a single low energy description of the theory, but I can always perform an SL to Z transformations and get an equivalent description. It's interesting to note also the central charge formula that we wrote needs to be consistent with this symmetry. So we saw, well, I told you that we had a classical formula for the central charge in terms of the coordinate A, which is the so the VEV of the scalar. and the classical holomorphic coupling. So clearly this formula cannot be valid also at the quantum level, because tau is going to be transforming along the RG flow, it's running. But if you remember that classically, tau, it's, sorry, F is tau over 2a squared, then I noticed that a dual in this case is just tau times a. So tau classical times a, I can think here to replace as a dual. Okay, so the proposal by Cyber-Witten is to modify this formula for the central charge in this way. So now instead of tau times a, I have a dual. So this formula makes sense also at low energy. And this formula is also invariant under the action of SL to Z, because now if you perform one of these SL to Z transformation that is mapping the theory to a dual theory, you act on the vector of a dual A coordinates with an SL2Z matrix. And similarly, you want to act on the charges, which since this is an electromagnetic duality, they are going to be rotated by as by a matrix which is the inverse of the SL2Z matrix, which is acting on the periods. So in this way, the central charge, it's invariant under the action of this duality transformation. And this is really what we want, right? Because the central charge is something that has to sit in the algebra and should know nothing about the low energy dynamics and its different possible descriptions. So it has to be invariant under this transformation that brings me to one description to the other. So this transformation is going to act indeed transforming electric charges into magnetic charges and transforming the coordinate a dual into a new set of coordinates in terms of the same SL2Z matrix. So I introduced this other fact, this invariance, sorry, this possibility of coming up with equivalent descriptions of the low energy effective action to solve, okay, the problem that we had some minutes ago. Remember, we were stuck with the problem that if I claim that there is a unique description, I run into the problem that the prepotential would predict a coupling which is not positive everywhere. So I had to a little bit scale down my expectations. So I cannot claim that I can find a unique description in terms of a unique holomorphic function everywhere in the moduli space. I need to have local descriptions. And this is good because also I know that now I have the possibility of finding dual description acting with this duality transformation. So what we expect is that if I go to a different region in the moduli space, maybe I will have to use a different sets of fields to describe the physics in that region. And that's perfectly okay, because it's also solving us the problem that there is not a unique description valid everywhere. So now we need to combine these two things together. So the way, I mean, these things come together is the following. So we we want to describe the theory locally around the potential singular point, the singular points in the moduli space, which, however, we still have to understand. So for sure, we think we understand what's going on in the region where U is large. So we look at the situation around the point at infinity. So let's focus in this region. So we are in the region where the U is very large. So this is the region so this is the region that we like and we think we understand. So here A is roughly the square root of 2U, and A dual, which is the derivative of the prepotential, is roughly I over pi. So I'm replacing A with square root of 2U. So I can ask what happens if I go around the point at infinity. So if I perform a rotation around the point at infinity. So this is clearly showing that A and A dual are transforming with a non-trivial monodromy matrix. So A is gonna flip sign, and A dual, because of the log, is also shifting. So it will become minus A dual and also shift by 2A, as you can see, because you have U in the argument of the log. So I can summarize saying that the monodromy at infinity is a matrix which is acting on A and A dual taking them to minus A dual plus 2A. And we notice, in fact, that this monodromy matrix is precisely an element of LCL2Z. So there is a monodromy. It means that there is a branch cut. And so if this is the point at infinity, there is a branch cut. And the branch cut must end somewhere. So the possibility, the first possibility is that since we always have been thinking that something is going to go wrong at the origin, we can try to think that maybe the point is that there is a branch cut connecting the point at infinity and the point at zero, where indeed we were expecting a singularity. But basically, this is cannot work. And the reason is that if you do a monodromy at infinity, this is basically the same monodromy that you do in the opposite sense around zero. So you have that the monodromy at infinity is basically the monodromy in zero. But then you see that under both monodromy at infinity and in zero, A flips signs, but A square is not flipping sign. So basically, if A is invariant, would be well, A square will be globally defined. But this is not going to fix, unfortunately, our problem of not having a description which is valid everywhere in the moduli space. So Cyber-Witten argued that this cannot be enough. We need to find something more complicated. We need to have a more complicated monodromies to solve the problem of the non-global definition of our low energy effective action. So the next possibility, the next minimal possibility is that there are two singular points at finite u. Now, remember, there is a symmetry in the moduli space. It is a remnant of the U1R symmetry. So it means that if there are singular points, they come in pairs. So if I need to have two singular points at finite u, 0 cannot be part of the game. And this is quite a blow, because we were thinking that classically u equal to 0, it's the point where we have singularity in the moduli space. Instead, we understand that at the quantum level, u equal to 0, it's a point which is perfectly regular. So now we're working under the hypothesis that there are two singular points which have to be u and minus u. I'm calling it u singular. So there are two singularities at finite values of u. Then we need to understand what is causing this finite u singularity. So we can again think that the problem is still due to the fact that maybe at these finite points, it's where A goes to 0. Okay, maybe it's possible that A goes to 0 and we have unbroken SU2 because I'm not undergoing Higgsing. So if we are not undergoing Higgsing, then there are these non-abelian massless gauge bosons that can be responsible for the singularity. However, there is an argument given by, well, Cyber-Witten argue that this is also not what's going on. So a reason it could be that to rule out this possibility, the possibility of massless gauge bosons is ruled out. The argument, if you want, can be phrased in this way. So for A equal to 0, we have SU2, which is a theory which is asymptotically free. And we expect, by asymptotic freedom, a free superconformal fixed point in the UV. And in this superconformal theory, we will have n equal to superconformal field theory. There is a relation between the dimension of an operator and the R charge of an operator. Remember, we have a similar relation in n equal 1, then there was a different factor. There was a 3/2. In the case of n equal 2 superconformal field theory, this is the relation. Then, if we live in this superconformal field theory, then trace phi square, which is our coordinate u, will have dimension 2. So this is u, okay? So the point is that, can it be that this object is non-zero? Because we are claiming that we sit at points where u is finite. If u is non-zero, it means that we are giving a VEV to something which has a mass dimension, because this guy has mass dimension 2. And this would spoil scale invariance. So it cannot be that we sit at a point where u it's finite, as we are saying here, and we have non-abelian gauge bosons that are driving the theory to a free point, where basically the only field that would be entitled to be non-zero are fields with without breaking scale invariance, are fields with zero mass dimension. So it's not possible, okay, that basically the responsibility of the singularity at this point is due to A going to 0, implying non-abelian SU2. So it is not due to A going to 0. So what else can be going on at this point? So what can be the physical origin of the singularity at these points u, s, and minus us? Well, now we need to go back to the observation that we had at the beginning of this lecture regarding the presence in the spectrum of other particles which are massive, and those are the monopoles, which are massive and carry a magnetic charge. So Seiber-Witten propose that at u equal to us, this singular point, a monopole become massless. So monopoles sit in hypermultiplets. And their mass, as we mentioned earlier, it's fixed by the fact that they need to be sit into short massive representations. And now we have our non-perturbative version of the central charge. So a monopole has a 0 electric charge and magnetic charge equal to 1. So the mass of the monopole is proportional to a joule. So the monopoles become massless when a dual is going to 0. So the assumption of Seiber-Witten is that at u equal to us, monopoles become massless. And a dual, which is the mass of the monopole, is going to 0. So it's totally different from what we were expecting classically, where we were thinking that there is a singularity at u equal to 0, where a is going to 0 because we have an unbroken SU2. And since we want to recover that in the classical limit, the singularity at this point US and similarly minus US is going to 0 to this classically singular point, this singularity has to be located in a position which is proportional to the strong scale lambda. Okay, so now there is an hypothesis of what's causing the singularity at this point. Now we need to understand how to get the physics. So this is why we need the dual description, because knowing that the monopoles are going massless would not be really helpful because we would not need how to write down a Lagrangian for the monopoles. But the idea is that if we use our dual description of the theory in terms of dual fields, then the monopoles become like electrons, like ordinary electric hypers for the original theory. So monopoles couple to the S-dual fields, where S is this transformation that I forgot to give names. This transformation is typically called an S transformation that takes you from the set of fields phi dual and phi to minus phi and phi dual. So the monopoles, the idea is that they couple to the S-dual fields, which are phi dual and the dual field strengths as electrons to phi and W. Well, electrons are ordinary, sits in ordinary hypers. It means that close to this point where the monopoles are becoming massless, I can have a dual description of my theory as a theory where I have only U1 gauge fields and electrically ordinary hypers. So basically, at this point, I have a description in terms of a supersymmetric n equal to super QED, where the role of the hypers is now played by the monopoles. So in this super QED, now I know everything, right? This is a infrared free theory. So we know how to write for example, the holomorphic coupling. So we know that the beta function of the dual coupling will be that of QED. So notice it is positive. And then I can calculate the dual coupling. Here, as usual, I'm using a dual for the scale when I do the integration of the beta function. Okay, so I am in this dual QED, but if I use the dual variables, it's really an ordinary QED with a positive beta function, and then I can construct the dual holomorphic coupling, and then I can keep going. I can construct. I can think that this dual coupling is going to be minus dA in the A dual, and integrate these to get A. So in this region, you see that A dual is measuring the mass of the monopole that is going to 0. So it's going to be roughly like the distance from the singular point. And A is going to be what I just wrote, which in terms of U is going to scale in this way. Okay, so the picture is that if I want to describe what's going on around the singularity, close to the singularity US, I need to think in terms of an alternative alternative dual description of the theory, where I have monopoles which are hypermultiplet, but they look like ordinary multiplets if I use the dual variables. So I have just an ordinary supersymmetric QED, which is a stupid infrared free theory for which I can calculate the gauge coupling, and then I can calculate A dual and A, and they will have this form, which is completely dictated by the one loop behavior. So I can also calculate the monodromy around this singular point. So now if I encircle the singular point, if I go around this singular point US, then by this expression that I wrote, I can calculate what happens to A dual and A. Then they will go, basically A dual will not change, whereas A will shift by 2 A dual. So the effect of this monodromy can be summarized by the action of a monodromy matrix. So the monodromy matrix around the point US is going to be this one. Good. So I don't need really to do more work to describe what's going on at the other singular point, because now, so that's my U plane. There are the two singular points. And you see that if I know the monodromy MUS, and I then know, because we have already discussed the monodromy at infinity, the monodromy around this other point, minus US, it's going to be written in terms of the other two monodromies, because the monodromy at infinity is going to be the product of the other two monodromies. So I know the matrix implementing the monodromy around the other singular point. So the question, to complete the physics picture, I need to understand what's going on at the other singular point. So the guess by Cyber-Witten is that at this point, it is a dion that is becoming massless. So the dion, it's a particle with electric charge 1 and magnetic charge -1. well, in general, dion has both electric and magnetic charge. So the hypothesis by Seiberg and Witten is that what's going on at the other singular point is that a particle which this charge set of charges is becoming massless. And one can check that this is correct, because if you act with the monodromy matrix around this point minus US, which is we just determined, so if you act on the vector 1, -1, so in fact, this vector of charges should be left eigenvalues of these matrices. So you can check that basically A minus A dual is left invariant under the monodromy. So this is the good coordinate that is left invariant by the monodromy around the point US. So that's the good vanishing coordinate, telling us which is the particle going massless. So summarizing, let's see if we recap what's going on. So we have our moduli space. Now let me draw it as a ball. And there is the point at infinity. And here we understood everything in terms of the prepotential, which we wrote using that the low energy effective action is just U1, is just a U1 theory. Then we have two other singular points. And at this point, we have a description in terms of a dual prepotential, where we have dual super QED with monopoles becoming massless. So in this phase, A dual is going to 0, is the mass of the monopole, is the vanishing coordinate. And then there is this other region where we have instead a description in terms of another phi dual, which is basically by the U into minus U symmetry, is just the same function that we had at the US point, but now the vanishing coordinate is A minus A dual. So here we have again a super QED with dions becoming massless, and the mass is proportional to A minus A dual going to 0. So that's, you see, to make things work, I need to use different descriptions related by the duality transformation of the theory. So I don't have a unique low energy description that is good everywhere, but I need to choose the good sets of degrees of freedoms, the good variables to describe the theory in each phase. Now you may complain that I really haven't completely solved the problem, because here in each patch, the prepotential we have non-perturbative corrections, and I did not fix the non-perturbative corrections for the electric theory. I only basically looked at the one loop parts in each patch. Now the amazing part is, the amazing bonus of the Seiberg-Witten solution is that the non-perturbative corrections in each region can also be totally fixed. So you see, this description here is based on our physics arguments. It's only given in terms of one loop parts, and we argue what is the behavior at one loop close to the singularity. And we got to this point just using physics arguments. Now, basically, our problem is that we still need to fix the non-perturbative parts, which complete these functions, this prepotential function. So in fact, now our problem is a math problem. So this math problem is that we want to find the multivalued function A as a function of U and a dual as a function of U, which so far we know them only locally in each region of the modular space, but we want to find them everywhere, knowing their behavior at the singular points. Their behavior, basically their monodromies at the singular points. So what are these singular points? So we know that as U goes to infinity, in this region, A is proportional to the square root of U, and is basically going like I square root of U over pi log of U over lambda square. Basically I over pi A log A over lambda square. When U goes to lambda square, which is US, then A instead, well, a dual now is the vanishing coordinates, and A goes like I over pi, a dual log of a dual over lambda. And then there is the other singular point. Here the vanishing coordinate is A minus a dual. And this goes like A minus a dual log of A minus a dual over lambda. So we are trying to find functions A and a dual as a function of the U parameter everywhere in the modular space, knowing how they transform under monodromies at the singularities. And we want a requirement. We want that the imaginary part of tau, which we calculate as the derivative of the A dual with respect to A, is positive, because that is basically what brought us here, because we want to have the gauge coupling 1 over G square is positive. So in this way, the problem is formulated as a standard math problem. It's basically a Riemann-Hilbert problem. And the point is that you can fix uniquely, actually, these functions A and a dual by looking at the asymptotic behavior. And indeed, the solution to this math problem provided by Seiber-Witten is very nice and elegant, and it is given in terms of the Seiber-Witten curve. So the idea is to take an elliptic curve. We can introduce an elliptic curve, which we can write down. So this is actually a family of elliptic curve with parameterized by the parameter U. This is basically a torus, and the modulus of this torus is the dA dual in dA, which we want to understand in terms of the periods of this curve. So the way to think about this torus is simply to think of it as a obtained by gluing two complex planes by two branch cuts. So imagine you have two complex planes, and you have branch cuts. Then you can think that this is just a torus where you have squashed the cycles. So these are the cycles of the torus, and they are here squashed into the cuts. So more precisely, what we are doing here, we are choosing a specific selection of branch cuts, which of course they are related to the singularity in the U plane that we discussed. So we are taking a branch cut that connects the two singular points, lambda square and minus lambda square, and another branch cuts from the point U to the point at infinity. So we are going to glue these two complex planes through these cuts. Then I will have these contours that encircle the singularities, which become the cycles of the torus, which realize by doing the gluing through the cuts. So we'll have this green cycle, which is the one corresponding to the contour encircling the cut running between the two singular points. And then I will have this other cycle, let's call it the B cycle, and let's call this other one the A cycle. So on this elliptic curve, I can define a holomorphic differential which is going to be x minus lambda square, x plus lambda square, x minus u. And I can integrate this holomorphic differential over the periods of this curve. And this defines the modulus of this elliptic curve. I'm using T of u to say that that's the modulus that you construct in this way, starting from the holomorphic differential. And this is clearly positive for this curve, if you do an endogenerate torus. So now what the idea is that we want to relate this construction to the problem that we want to solve. So we want to find an integral over the contours that are calculating for us directly A and a dual and identifying the torus modulus tau u with the holomorphic coupling tau. So basically we want to define another differential up to exact forms such that we want to find the Seiberg-Witten differential, which is defined so that the integral of this differential over the A cycle calculates for me A, and the integral over B calculate for me A dual. And then I could define, well, I can define tau as dA dual in du over dA over du, and identify this with the tau of u, that is what we are guaranteed that is a positive, has a positive imaginary part. So there is some steps which I don't have time to go through in great detail to how to basically nail down the form of this differential. But basically, the idea is that you want to interpret the day dual in the U is just d lambda in the U, and the A in the U, it's d lambda in the U, so that's true. So you can try to look for a solution of this type for the lambda and integrate in the U, and then fix this function, this possible function f of u by to reproduce the expected behavior at the singular point. So you can do this. This is pretty simple, and then you can fix the form of the Seiberg-Witten differential, which is it's square root of 2 over 2 pi x minus u s square minus lambda square. So once you have the correct differential, then you simply use this formula to calculate an A dual, and then basically you have solved the problem. So A as a function of u will be just the integral over the A cycle. So the A cycle, remember, is the one that is going around the cut. I can basically squeeze this contour into a contour that goes on the cut. This is basic complex analysis. So you can write this as an integral between lambda square and minus lambda square. And similarly, you can calculate A dual as an integral going from lambda square to u. And the amazing thing is that these integrals, well, can be done. So you know them exactly in terms of hypergeometric functions. They are both so basically you can say that you have solved the model. So in particular, I'm just so A of u is going to look something so lambda square plus u square. So this minus a half 1, 1, they are the coefficient of the hypergeometric. And then there is a similar expression for A dual of u. So see, that's the global definition that we were looking, sorry, that's the definition of A dual valid everywhere in the moduli space. And then I can take this special function and expand it in each patch and find the form of the prepotential in each region. So let's look at the U infinity point. So here, A, you can find that A indeed is going like square root of U, but then you find all the correction that you have by expanding the hypergeometric for large U. And then you can invert to find U as a function of A, and you plug it in a dual. So you find a dual as a function of U, which is a function of A in this way. So you get a dual as a function of A, which is the derivative of the prepotential with respect to A, and you integrate to find the prepotential and now all these coefficients that were hanging there, waiting to be fixed, now they're fixed. They are fixed by the expansion of this hypergeometric function. So now you really fix completely the solution in the U to infinity region. And you can repeat the argument if you go close to lambda square. Now you have that a dual is proportional to U minus lambda square. And you invert to find U as a function of a dual. And then you calculate A as a function of a dual. And you integrate to find F dual as a function of a dual. And you will fix completely also F dual in this region. And then you will do, of course, the same in the other region. So if we use the correct set of variables, we know we can determine F everywhere in the U plane. But you cannot use the same set of variables and the same, meaning the same physics description everywhere in the model space. So unfortunately, my time is running up, but I still have a couple of things to tell you. So the first one is, well, one important application of this construction that was in the original paper by VIII was as a model for confinement. Actually, the VIII was proposed to be the first theory displaying a model for confinement. So we'll try to summarize their argument in a moment. And maybe before I want to make another comment about the important development that followed this result by VIII. So VIII managed to construct the prepotential everywhere in the U plane using this construction of this, solving this problem, this monodromy problem. They managed to fix this contribution due to instantons. There is another way to get instantons. So can also be derived via localization. So this is a completely independent construction to calculate the contribution of instantons to the effective action, which is not resorting to holomorphy, and as we did here. And basically, it has been possible eventually to match the result by Seiberg-Witten with the result from localization. And this is the result by Nekrasov from 2002. Basically reproduced prepotential, the Seiberg-Witten prepotential from instanton counting. And well, of course, this result came not out of the blue. There was previous work by people like Lozev, Nekrasov himself, and Shatashvili, and also work with Moore by the same people, where they were preparing the field to this development. So they were learning how to integrate over the moduli space of instantons. So eventually there was this result by Nekrasov where he managed really to reproduce these results by Seiberg-Witten, in particular the contribution of the instantons. So matching the result that was obtained by the holomorphic and this use of the geometry of elliptic curve. And so this was really a very important development, which I don't have time to discuss. So maybe I shall use the remaining minutes to say something about the other important physics statement that was done in the paper of Seiberg-Witten. So on top of solving completely the theory in the sense to being able to find the prepotential in each region of the moduli space, they also argue that this is a model for confinement. It's confinement due to monopoles. So the idea goes as follows. So, so imagine, so in pure SU2 n equal to Super-Young Mills, turn on a mass of a large mass, larger than the strong scale, for the chiral field phi. So if phi, which is the chiral into the vector multiplet, become massive, you break n equal 2 to n equal 1. Right? You just kill the chiral multiplet into the vector multiplet, so you are left only with n equal 1 vector multiplet, so you have n equal 1 Super-Young Mills. And we know that n equal 1 Super-Young Mills has two massive vacua gapped remember the story with the Gaugino condensation. So in this phase, we have, well, when we break to n equal 1 Super-Young Mills, we have confinement, and the theory has a gap. So there are no massless states left. And basically because the non-abelian gauge boson is forming these global fields which are massive. Now, if instead we turn on a mass which is smaller than the strong scale, basically I am not dealing with n equal 2 Super-Young Mills, but as we discussed, I should be using the low energy description of the n equal 2 theory. So in this low energy effective theory, we are basically saying that we are turning on a mass for U, which is the lowest component of the chiral multiplet. Capital U. So there are basically two possibilities. It can be that I'm in the large U region, so if you are in the large U region, then we have U1 is this U1 theory with no charge fields, where you only have the chiral multiplet, which is in the adjoint. So if I turn on a mass for U, basically nothing really interesting is going on. So maybe it can lift the vacuum. But we cannot have a mass gap. So there is no way that if I turn on this mass for U, I mean, this mass for U maybe gets rid of the scalar in the chiral multiplet, but the vector multiplet, the U1 vector multiplet stays massless. So I cannot have a mass gap in this way. So I cannot explain the confinement as we have in n=1 case by this logic. So it cannot be explained if I imagine turning on the mass in the low energy theory in the large U region. So this doesn't work. But if we are in the, if we are close to the point where the monopole become massless, then something interesting can happen. Because now remember the description at low energy, we have supersymmetric QED. So now we have charged particles, which are the monopoles. So the superpotential now will be of this form. You will have, if you remember how the coupling in an n=2 theory, how the hypermultiplet couples to the vector multiplet, remember they only couple to this cubic term. So we have a coupling between this, the chiral multiplet and the vector multiplet and the two hypermultiplet. So these M's are the, I'm using capital M to indicate the hypermultiplet in which the monopoles sit. So now if I add a mass term, okay, so now if I add the mass, which is M times U, this is the mass breaking 2 n=1. So this now I think this chiral multiplet U as a function of the coordinate A dual. Then you see that now W plus dW has this form, and I write down the F terms for this theory. I write the equation of motion. So when I don't turn on any mass, the equation of motion will only telling me that the monopoles don't take a wave. But when I turn on this mass that is breaking to n = 1, then the equation of motion is telling us that m equal to m tilde equal to stuff, which will be the derivative of u respect to a dual. Anyway, this is non-zero. So monopoles take a wave. So a situation in which monopoles take a wave was a scenario that was at the time where the Sybert-Witten work was done, and before was considered a promising scenario to explain confinement. And the mechanism that people were invoking was the dual Meissner effect. So, well, time is up, really. I'm actually going over time, but in a word, you can say that the Meissner effect, the original Meissner effect, which explains, is the mechanism that explains why in a superconductor you don't have, below the critical temperature, you don't find a magnetic field inside a superconductor, can be explained by a Higgs mechanism, where basically you have that scalar, which symbolize the Cooper pairs, develop a wave. The U1 gauge group is broken, and as a result, the magnetic field solves a massive equation, which explains why it decays exponentially inside the superconductor. In particular, if you have this superconductor where you don't have a sketch of this idea is that you have a superconductor and the magnetic lines cannot really enter below the critical temperature. If you try to put two sources of magnetic to magnetic charges in this superconductor, then the lines of magnetic fields are squeezed in a flux tube. And the force between these two test magnetic charges, which is basically the tip of a solenoid, increase linearly. So that's the Meissner effect. Now you want to do the dual. So now in the dual configuration, it is the electromagnetic field that is expelled, and it forms flux tube responsible for confinement. So in this configuration is not the object that is condensing is supposed to be the monopoles rather than the electrons that would sit into the Cooper pairs that then would condense and produce the Meissner effect. So this idea of dual Meissner was advocated as a potential mechanism for confinement in gauge theory, and in this situation of the n = 2 theory, in the close to the point where you need to use dual variables and you have light monopoles, then that seems what to account for the confinement. I think, yeah, there were other things that I wanted to discuss, but I think I really went over time, and maybe we can use also the time for the office hour this afternoon if you want to discuss more. So yeah, please feel free to ask questions.